Always. Okay, great. Welcome. Good morning. So what we're going to do is today is continue talking about different types of reactions that occur in water. So we're going to look at our second type of reaction today, and we'll go a little bit beyond that as well. There's a particular problem in ALEKS that I do want to spend a little bit of time on discussing how you classify reactions, because there are different ways to classify reactions. Last week, what we did was we looked at initially at the properties of water and how things dissolve into water. We essentially had two different groups of substances that could dissolve well into water. We had the ionic compounds, such as sodium chloride or lithium chloride. We also had the alcohols and the sugars. And there's actually a phrase that people often refer to when it comes to why sugars and alcohols dissolve into water so well. And it's called like dissolves like, meaning that if two things are very similar in structure, they have a tendency to be able to mix very well with each other. So alcohols and sugars both have these OH groups, which is essentially the structure of water. Water is H2O. So for that reason, the water is like alcohol. Water is like a sugar. So it is able to dissolve them. Okay. Then we looked at a type of chemical reaction, which we called the precipitation reaction. And the precipitation reaction was the case where you take these ionic compounds and you dissolve them into water, and they will mix, and they will form, sometimes will form a insoluble precipitate, meaning an ionic compound that doesn't dissolve into water. And if that happens, then we see a solid formation, and that's called a precipitation reaction. So we used what were called the solubility guidelines to look at predicting whether a particular compound would be insoluble in water, not soluble in water, and which ones would be soluble in water. And what we found was that certain compounds, for example, sulfides or carbonates or phosphates, tend to form precipitates. So when we look in water, if we see something that's a solid, it tends to be things like carbonates or phosphates or sulfides. Other types of ionic compounds are very soluble in water, so we don't tend to find them in the form of solids in water. So for example, sodium chloride doesn't really form a solid in water. It dissolves into water, so it's a soluble compound. So examples of the examples of the precipitation reactions were, things like bone formation or, seashells, for example, or kidney stones was an example as well. What we're going to look at today is the second category of reactions, which are called acid-base reactions. And this is a very large topic in chemistry because acids and bases have particular activities that can be used to synthesize compounds, break down compounds, make reactions go faster. All sorts of things go on with acids and bases. So we're just going to cover a tiny bit of it today. If you take the second semester course, we have a whole 2 chapters dedicated to acid-base reactions and acid-base chemistry. So here we're just going to cover a few pages and get you some introductory topics. So let's take a look at acids and bases. I'm going to introduce them first. And then what we'll do is we'll look at an ALEKS problem where you're classifying reactions and recognizing what types of reactions are present in circumstances. Okay, so let's talk a little bit about acids and bases. Let's begin with the idea of an acid. There's different ways of defining acids and bases. Isn't it interesting? So there's not just one way to define them. We can define them in different ways. And one way is to say that an acid, I'm going to use the the term substance is a substance. Now, in chemistry, the term substance typically means something that is different from everything else. So, for example, if you have a aspirin in the form of a tablet, the aspirin, the compound, which is acetylsalicylic acid, is a substance. It's a chemical substance. The water that you drink with that aspirin, the water itself is a substance. So a substance is just some kind of pure material. It's typically a compound, but it could also be an element, right? So if I have a piece of gold, that's a substance as well. So an acid is a substance that when dissolved into water, okay, so water is here, right? We're talking about water, produces the hydrogen ion, H plus. And then I'm going to put in parentheses that it's also called a proton. We often refer to the hydrogen ion, which has the formula H plus. We refer to it as a proton. And the reason for that is that a hydrogen ion is a hydrogen atom in which its electron has been removed. So if you take the electron off of a hydrogen atom, the only thing you're left with is a proton. So it's often referred to as a proton. So H plus is the formula. It's called a hydrogen ion. And the hydrogen ion has a diversity of chemical activities. It's able to do all kinds of interesting things that as you go on, particularly if you go on to take things like organic chemistry or biochemistry or molecular biology, the hydrogen ion ends up being a very important species, a very important substance in terms of making reactions occur or stopping reactions, all that sort of stuff. Okay. So that's called the hydrogen ion. So any substance that if you put it in water and it forms a hydrogen ion, we call that an acid. So an example of that would be hydrochloric acid or hydrogen chloride, actually. So I'm going to put this as a gas. So this is called hydrogen chloride. It's a gas. So HCl, hydrogen chloride. If you dissolve it into water, so I'm going to write it this way. I'm going to put the water above the arrow. So that the meaning of that is that you're putting the hydrogen chloride into the water. So it's a gas. So you'd have like a little gas tank with a little hose coming out of it, and you would bubble that hose, the gas, into the water. And what happens is the hydrogen reacts with the water to form the hydrogen ion, which is dissolved by water. And then you also get a chloride ion as well. And we're going to call them aqueous because they're now dissolved in water. And in practice, essentially what happens is the hydrogen ion, I'll draw a little circle around it, is, just like with other ions, like sodium ions, it is surrounded by these water molecules, right? And we're going to represent the water molecules as little dipoles, right? So all these water molecules are trying to interact with the positive charge of that hydrogen ion. So it gets dissolved into the water, okay? Now, it turns out the hydrogen ion is a highly energetic particle because it's just a proton. So in a sense, like you're talking about a subatomic particle. And so a subatomic particle has a lot of energy if it's all by itself. And so you don't find them very often. So for that reason, the water molecules be very strongly attracted to that positive charge, more so even than with, say, a sodium ion, okay? Chloride ion, same thing. The chloride ion is going to get surrounded by the water molecules. In this case, the water molecules will turn the opposite direction so that the positive charges are interacting with it, right? But essentially the same thing. Sorry, I didn't draw that one very well. Plus, minus, okay? So for that reason, many acids, including hydrogen chloride, dissolve very nicely into water, okay? Because it's essentially, we're talking about these small ions that can be surrounded by water molecules, solvation, right? Remember we call this solvation? Solvation is the case where these water molecules surround the ions, right? They're solvated. They're also hydrated because it's water. we say that these ions are hydrated, surrounded by water molecules. Okay. Okay, so that's an example. Now, when an acid is dissolved into water, it's typically given a name to call it an acid. So as a gas, hydrogen chloride, we're using a naming system of you name the first element and then you name the second element and you change the ending to IDE. But once we recognize that it is an acid, we then give it a different naming system. So this one, once it's dissolved into the water, so I'm going to write HCl, we call it hydrochloric acid. Okay, so when you see these names where you see hydro at the front, hydro is usually referring to something being an acid. And then ic, you'll see that often. So hydroic acid, that would be an example of an acid. Okay, so here's another example. You look and you see a hydrogen there, right? And then there's, say, a bromine. Oh, there's a bromine, right? So it kind of sounds, it's a little bit like HCl, right, in terms of its form. So this one, same idea. We call it hydrobromic, right? So we're just changing the element here. It's not chlorine, it's bromine. So it's hydrobromic acid, right? So hydroic acid. Okay. So those are kind of the simplest of the acids, the ones where you have a hydrogen with one nonmetal. So HCl, HBr, HI. You can do one more here, HI. This is iodine. I is iodine. So hydroiodic acid. Okay, iodine, right? So same idea. These are often referred to as, binary acids, or there's other names for them as well. But essentially, there's just two very simple parts. You got your hydrogen and then your nonmetal. So hydrogen, nonmetal, hydrogen, nonmetal. And the most common of these are the ones where you've got the halogens. The halogens are the group 7A elements. Okay. But there are other types of acids out there as well. There are more complicated acids. There are acids that don't have just, like one atom attached to them, like chlorine or bromine or iodine. There are acids that have polyatomic ions associated with them, and they are also acids. So let me give you a few of those, just sort of common ones. Okay. So ones including the polyatomic ions, you'd see something like HNO3. So again, the format is you get a hydrogen in the front and then some non-metal coming after it. But in this case, it's got this polyatomic ion in here, which is called the nitrate ion. Okay. So really what you have here are two parts. You have the H plus, and then you've got the NO3 minus. Okay. So H plus and NO3 minus. Just like over here, you've got the H plus and you've got the Cl minus, right? So, physically, it's kind of the same thing. It's a hydrogen ion attached to a non-metal that has a negative charge. We often refer to that as the anion, right? Now, what's a little challenging about this is that you can have different acids that look kind of similar in their formulas, but there are little minute differences. Oops, sorry. That's not a minute difference. That's no difference at all. There we go. So here's a small difference here. It's got the hydrogen just like before. It's got the nitrogen just like before, but now it only has two oxygens. So that creates an issue in terms of identifying them, right? Because if you think of the acid as being hydrogen, nitrogen, and oxygen, well, we now have two of them. So they're going to have different names, and they are actually different substances. They do exist. So here's the way we deal with that in terms of a naming. Okay. You don't put hydro for the polyatomic ion. So if it's got a polyatomic ion like this, you don't use the hydro. You take the name of the polyatomic ion. So this polyatomic ion is nitrate, right? NO3 minus is the nitrate. That's the name of that polyatomic ion. And you change it to ic, and then you put acid at the end. So nitrate becomes nitric. So see, we're changing the ending ATE to IC, and then you write acid after it. Okay. So if you're looking these things up, you find an acid, what you do is you look up the polyatomic ion, so nitrate, NO3 minus, and then if it ends in ATE, you just change it to ic acid. So nitrate becomes nitric acid. So this right here is nitrate. This right here is nitric acid. Okay, so 8 to ic, sometimes we say. Now, this next one over here, it also has a polyatomic ion with nitrogen and oxygen, but it only has 2 oxygens. And there is a system to this. The system is, if you take an oxygen off, the polyatomic changes its name from 8 to ite. Okay, so if you have 3 oxygens and that's 8, 2 oxygens would be ite. So this is really nitrite. That's the name of that polyatomic ion. And then the naming system is, if it ends in ITE, you change it to us acid, OUS. So this becomes nitrous acid, right? So with the hydrogen, sorry, I meant to draw that over there. With the acids, ite becomes us acid. So the polyatomic ion is ite, the acid is us acid. 8 becomes ic acid. Okay. There's a if we come up to it, we'll look at it as well. There's a couple of other ones. There's hypo and there's per. So if you have even more oxygens, it's hyper essentially. Hyper meaning even more oxygen. We would call it per acid. And then if it had even one fewer, it becomes hypo, which means under. Hypo, so it'd be hypo us acid. Okay, well, if we come to those, we'll look at those. Okay, so these are acids just like the HCl and the HBr and the HI. So when you look at the names, if you're looking at names of acids, if you see hydro, well, that tells you right there it's one of these acids that just has an element next to the hydrogen. But if you see no hydro and it says ic acid or us acid, that's telling you you've got a polyatomic ion associated with the acid. And they behave very similar. So if I take HNO3 and I dissolve it into water, same thing. You can get this H plus, and you're going to get the nitrate, NO3 minus. So they behave just like the, relatively like the, these acids over here, monoatomic acids, I guess you call them. Okay. And there are many of them, right? So let me make you a little list of some of the common acids. Let me just save this one. So some of the common acids. So we already have a few, right? So I'm going to start with the simple ones here. Okay, so hydro, right? If it only has one element following the hydrogen, you're going to have hydro in the front. So not hydrogen, sorry, hydro. And then you take a look at the elements. So it's fluorine, so fluoric acid. Okay, so it'll be ic, so hydroic. Hydrochloric acid. This one is the one that's in your stomach. It's very active in your stomach. And if you happen to like throw it up or burp it up, it irritates your esophagus. It's painful. It burns because of that strong hydrochloric acid. Hydrobromic acid. And then hydroiodic acid. All right, so there's 4. And then you got the ones with the polyatomic ions. So we did a couple of those, HNO3. Sorry, nitric, right? So if you don't see the if you don't see the hydro, that's telling you it's a polyatomic ion associated with the hydrogen, with oxygen, almost always with oxygen. These are sometimes referred to as oxoacids because they have oxygen with them. And then if there's one fewer oxygen, you change it to us. So nitrous acid, okay? Here's another pair. This one's a little different in that it has two hydrogens, right? This is called a diprotic acid. I'll write that in parentheses. Well, actually, let me write the name first. Sulfuric acid. So notice no hydro. This is called diprotic because it has two hydrogens. And that's something you really cover in Chem 12 and at the, early in the course there. And then you can also, I'm just listing ones that exist. These are just ones that exist in nature, not making them up. So the next one, if you take an oxygen off, again, you change it to us acid. So this one becomes sulfurous acid. And again, this one is also diprotic, right? Because it has two hydrogens, okay? So this one actually, in a sense, loses two hydrogens, although there's some details in that discussion. Another common one involves phosphorus. For those of you that have taken biology courses, there's this acid where you have three hydrogens and it's got a phosphorus in it, right? And that one's called phosphoric acid. This one's actually got three hydrogens, so we can refer to it as triprotic because it's got three. And these all together, we call them polyprotic because they can have two or three, more than one, essentially. All right, so those are called polyprotic acids. And if it has two or three, there aren't really any out there with four, although in theory, a protein which has many, many different amino acids could have even hundreds in there, hundreds of hydrogens. But for the most part, we don't deal with those in this course. So if you take an oxygen off, I've never actually seen this one. I've never actually worked with it. But if you take an oxygen off, then it's going to be changing to OUS, right? So this will be phosphorus acid. Okay, still triprotic, but it has three oxygens, okay? We'll draw structures of these when we get into Lewis structures later in the course. Here's another one that's important in terms of biology. It's also diprotic, but it has a carbon. So this one's called carbonic acid. Okay, this one's also diprotic. Two hydrogens. Now, in theory, you might be able to have H2CO2, which I guess would be carbonous acid, but I've never seen it. So some of these things, even though you might be able to think of drawing the formula, they may not actually exist in nature. Okay. So notice a pattern with these acids here. It's a hydrogen or maybe more than one hydrogen with a nonmetal, nitrogen, carbon, sulfur, phosphorus, and then a bunch of oxygens, right? That's a common kind of pattern among these acids. I can show you one more here. It's a monoprotic. It's only got one hydrogen. So this one looks like the one above it, but it's a little different. That's not Ci, it's not carbon iodine, it's Cl chlorine. So it's hydrogen, chlorine, three oxygens, okay? And this one is called chloric acid. And so again, it's just another example of the kind of pattern of these acids. Hydrogen, nonmetal, oxygens, and we'll talk more about their structures. We may need to get into their structures a little bit in this course, or not in this course, but in this chapter. So if that comes up, we'll look at their structures a little bit more. But that's kind of the pattern you see these. One group, hydrogen with a nonmetal. The other group, hydrogen with a nonmetal, and then a bunch of oxygens. And these are all examples of acids, okay? Let's take a look at bases. There we go. Bases. So bases, similar to acids, we can think of them as substances that dissolve into water and form the hydroxide ion. OH minus. Okay, so the acid was the hydrogen ion, H plus, sometimes referred to as a proton. Bases involve the hydroxide ion. They dissolve into water and form the hydroxide ion. And this is what's important about this is really the solubility guidelines. Because in order for something to form the hydroxide ion, it's got to be able to dissolve. So it's got to be soluble. So if you take an ionic compound that has hydroxide in it, but it doesn't dissolve, it's not producing hydroxide ions in the water. So here's an example. Sodium, right here, NaOH, that is a solid. And if you put it into water, it will dissolve according to the solubility guidelines into sodium and hydroxide. All right, there's your hydroxide ion. So the fact that it dissolves means that you're going to get hydroxide in the water, so that means it's a base. And the naming of bases is different than acids. We don't really have a naming system for them. We just call them by their ionic compound names. And so you name the metal, sodium, and then you name the non-metal, hydroxide. So it's, you know, it's not called like sodium hydroxide base, it's just called sodium hydroxide, because that's the ionic compound's name. Okay, so bases are essentially these compounds that have a metal and a hydroxide, and those two will break apart in water to form, in this case, sodium and hydroxide. So I'll make a list of them in a moment, but I want to point out that if the substance cannot dissolve, so here's an example. So iron 3 hydroxide, this is called iron 3 hydroxide. It looks like it might be a base too, but the problem is if you put it into water, it does not dissolve according to the solubility guidelines. So if it can't dissolve, it's just going to be a rock. It's just going to be a big solid that can't form any hydroxides. To become a base, something has to be able to produce the hydroxide in water. So this is not a base. Okay. So which ones are? Well, it really just comes down to the solubility guidelines. So the bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. So those 5, they dissolve into water. And then there's a couple of others. There's calcium. Calcium is in group 2, so it has a +2 charge, so it has 2 hydroxides. Strontium also dissolves into water, and barium dissolves into water. Okay, so it looks like there's what, 8 of them, right? So these you know, there's 8 of these bases that are soluble in water. So that means they produce the hydroxide ion. Okay, so any other metal, you know, magnesium or iron or nickel or cobalt or gold, if it's a hydroxide, it's not going to be able to dissolve into water. So you're not going to get hydroxide. So it's not a base. Okay, just these 8 here. Okay, now those are the typical bases. Those are the 8 that are most common. But I do want to point out a little bit, I have to give you a little bit more background in this. This idea of forming the hydrogen ion as an acid and the hydroxide ion as a base, that works for most compounds. But it turns out there's a group of molecules out there that behave as bases, but they don't even have a hydroxide in their formula. And so they're important. So we have to talk a little bit about them. So for that reason, I'm going to give you a second definition of acids and bases. So we'll call this definition number 2 for acids and bases. And this is based on the idea of reactivity. This is what's called a Bronsted acid and base. Bronsted -Lowry, Bronsted-Lowry acids and bases. And this is based on reactivity. So in this case, the acid is defined. The acid is a substance that can react with water to produce the H3O plus ion, which is called a hydronium ion. Okay, and a base is a substance that can react with water to receive the H3O, I'm sorry, to receive, oh, you know what? The hydrogen ion. Okay, so that's the base. Okay, so let me rephrase this acid. Acid is a substance that can react with water to produce the hydronium ion. Okay, I guess that's fine. And then the base is a substance that can react with water to receive a hydrogen ion. We'll go over this a little bit here. So here's an example of what I mean by that. If we take HCl and we bubble it into water, I'm going to write this a little bit differently. Instead of writing it as the hydrogen chloride dissolving into the water, I'm going to show it as actually reacting with water. Remember, when we write it this way, this means these are reactants. So they're actually colliding with each other and reacting. And here's what happens. This is what's believed to happen. When they collide, the hydrogen is transferred to the water, specifically to the oxygen. So what ends up happening is you end up with the chloride ion, right? Because if you take the hydrogen off of HCl, you just get chloride. And then the hydrogen goes on to the water and you get the hydronium ion. Now, why am I writing this as minus and plus? Why negative and plus? Because what I'm claiming is that the HCl is kind of like an ionic compound. Think of it like this. I'll write it in parentheses. H plus Cl minus bound together. So what's happening is the H plus is going to the water, leaving behind the Cl minus, right? So that's over here. And then the water is taking the H plus, and that's forming this hydronium ion. Okay. Now, what we would claim is that the hydronium ion, H3O plus, is essentially the same thing as the H plus ion. It has hydrogen in it. It has a positive charge, pretty much the same thing. Now, it's true, there's 3 hydrogens and there's 1 oxygen, but 2 of those hydrogens are part of water and 1 is part of the, well, oxygen is part of the water as well. But essentially, they're the same thing. So we have different names for them. This is called the hydronium ion, and this is called a hydrogen ion. But like I said, they're essentially, so I'm kind of drawing a, almost equal to, approximately equal to, they're approximately equal to each other. They're essentially the same thing. But it's a different way of looking at it, right? Instead of just saying that the HCl dissolves in the water to form H plus and Cl minus, we're now making a different claim. We're claiming that the HCl is actually reacting with the water. And the water is not just this thing that just surrounds things, ions, it's actually a reactant. It's actually active. And that's what we believe to actually be the case. So one thing to say is that this model here, which we call Bronsted-Lowry, it can account for all of the acid properties of the acids that we've looked at so far, HCl, HBr, HI, H2SO4, HClO3, all of those are inclusive in this, but it can also describe some more details of the chemistry. So for that reason, chemists typically like to use the Bronsted-Lowry theory. But now let's talk about the issue of the base. The base, I gave a slightly different definition here. I said the base is a substance that can react with water. Okay, so notice the acid here is reacting with water too. But a base can react with water to receive a hydrogen ion, an H+. Well, this is the hydrogen ion here, right? So by that definition, water is a base. Because think about it. What we did was we took the H2O, the water, it took an H+ to form hydronium. So the water is actually acting like a base in this case. We don't really need that theory to describe this reaction because the previous theory of just, dissolving to form ions worked. But there are bases that we need this theory to be able to explain. And the most famous of these bases is called ammonia. NH3, that's its chemical formula. Now, you've probably seen ammonia in cleaners, particularly glass cleaners like Windex. They typically use ammonia. You can buy cleaners that use ammonia. They're not as popular as they used to be because what happens is if you take ammonia and you combine it with bleach, which is something that people use to clean, the ammonia actually reacts with the bleach and you get this gas that can actually kill you. So for that reason, ammonia cleaners are not that popular, but they still exist. You can go to a 99-cent store and find your ammonia cleaners, okay? So ammonia is a relatively common substance, and it actually is a base, and it doesn't have any hydroxide in it. There's no OH in it in the formula, so how can this thing act like a base? In fact, looking at the formula, you'd be more likely to think that it's an acid because at least it has hydrogen in it, right? But in fact, ammonia is a base. And here's how it operates. Here's how it functions. When you take ammonia, and it's a gas as a pure substance, you buy it dissolved in water. So that's why it's in liquid form. It will react with the water. And here's what happens. The water actually transfers the H+. So I'm going to draw that up here. This H+ that I'm drawing here going to the ammonia is coming from the water. One of the hydrogens is transferring over. And when that happens, the nitrogen, the ammonia, now has 4 hydrogens and a positive charge. Since it's an ion, it dissolves into water. And then the water has lost an H+, so it is now OH-, and there's your hydroxide ion. So this chemistry is very interesting because essentially what it does is it says that if you take ammonia and you put it into water, your end result is you're going to have hydroxide, which means based on our earlier definition, anything that produces the hydroxide ion must be a base, right? It must be a base. So the ammonia must be a base. And one thing to say about bases is that they taste bitter. Okay, bases, they taste bitter, okay? So and the reason for that is the hydroxide ion. The hydroxide ion actually tastes bitter to your tongue. There's a part of your tongue that's sensitive to that. And part of the reason is that bases are dangerous. They can actually dissolve skin. They react actually with the fats in your skin, and then that's a very dangerous thing to happen. You want to have your skin protecting you. So for that reason, you don't want to ingest bases. We're evolved to avoid ingesting bases because the hydroxide can then just start dissolving essentially your digestive tract, right? All of the epithelial tissue in your digestive tract. So it's dangerous. So that's why your taste buds have a sensitivity to that. It tastes bitter, right? And for the most part, bitter, people don't like that taste. You can train yourself to like the taste, but initially you'll probably avoid that, right? So things like caffeine, for example, taste bitter. And they taste bitter because caffeine is actually a base and forms the hydroxide ion. It's not a very strong base, it's a very weak base, but it does form hydroxide ions, and that's why it's bitter. Okay. So there we go. So now we have a different type of base. So these are often referred to as the nitrogen bases. And again, if you're a biology student or a biology major, you're familiar with these nitrogen bases. They're very important in terms of life, right? So for us, we don't use a lot of biological molecules in this course. Ammonia is an example of a nitrogen base. Methylamine, CH3NH2. So this is called ammonia. This is called methylamine. That's a nitrogen base. So it's got that nitrogen right there, right? C2H5NH2. This is called ethylamine. There's actually a very interesting ring structure. We're not going to talk about these structures right now. So I'll just draw it like this just so you can see it. So that ring just has a bunch of carbon and hydrogens in it. We'll talk about it later in the course. This one is called aniline. But again, notice you got that nitrogen with some hydrogens there. So the nitrogen bases are compounds. And of course, this includes caffeine, nicotine, cocaine. I think morphine as well. Right. So actually, I'd have to check. So all these dangerous drugs like fentanyl and all of that, I have to check and see if they're actually nitrogen bases. They probably are. All of those are bases because of that nitrogen. So what happens is you dissolve it into the water, it reacts with the water, takes an H plus from the water, resulting in the water being converted into OH minus, which is the hydroxide ion. So therefore you get a base, right? So it's not a bad idea to think of water, at least when we're talking about acids and bases, as being kind of like this association of H plus with OH minus. It's kind of helpful to think of it that way. Think of it as having two parts. So this is sort of the part that acts like an acid, and this is the part that acts like a base, right? So if I take off the H plus, then you're left with OH minus, hydroxide. If I remove the OH minus, you're left with H plus, so it's kind of behaving like an acid, okay? It's not a bad idea to think of the hydronium ion, H3O plus, as being H plus with H2O, right? Think of it as two parts. You got the H plus and you got the H2O part. And then the water, you got two parts, the H plus and the OH minus part, okay? That can be helpful in terms of identifying what's going on, okay? So two different definitions of acids and bases. By the way, there's other definitions of acids and bases too. In Chem 12, we cover one more. And then actually, if you were to be a chemistry major and you took more advanced courses, there's actually even a couple other definitions of acids and bases. But for at least for us, it's just these two that we need to worry about, okay? So that was a lot of reviewing. That's 45 minutes of reviewing acids and bases. But if you don't know what an acid and base is, it's hard to kind of make sense of all this. So what I want to do now is I want to look at least one, but maybe two ALEKS problems, and then we'll do some more problems tomorrow in terms of classifying reactions and then looking at some acid-base chemistry. So what I'm going to do is bring up the first one. Oh, I'm sorry, I think I want this one. There we go. So I'll bring up this one. And what this one says is, hey, you've got, several types of examples, several examples here of chemical equations, right? They represent reactions, and we want to classify what type of reactions they are, okay? A little bit of this is actually covered in chapter 3 in the textbook, the last section where you're doing limiting reactants. There's a little discussion of combination reactions and decomposition reactions. But there's different ways to classify reactions. So I want to go through this because it's easy to get maybe part of it right, but this part of it as well. So let's go through it. The first reaction that's shown here, ooh, that's a mess, right? Look at that, CH3, CH2, 3, gas plus 8O2 gas to form 5CO2 gas plus 6H2O gas. So I hope you can see that as an example of combustion, right? We talked about that last week when we did chapter 3. We were talking about combustion analysis, actually, right? Combustion is where you take a hydrocarbon, so something with carbon and hydrogen. It might also have oxygen or nitrogen in it, but it's got to have carbon and hydrogen. React it with O2 to form carbon dioxide and water. And that's exactly what this is. So this first one right here is called a combustion reaction, right? Burning. Burning is a loose way of talking about combustion. Okay. Look at some of the other possibilities. You've got combination. We'll talk about that. Single replacement, double replacement. We've talked a little bit about double replacement when we did precipitation reactions. Acid-base reactions are often also double replacement. Decomposition, that's where something becomes simpler. It breaks up into smaller pieces. You're decomposing it. And then precipitation, we've looked at that already, right? And then you get acid-base. So we're looking at these different categories of different types of reactions. There's another type of reaction called a reduction oxidation, which is not listed here because that's a later section in the chapter. But we'll add that. That'll be an additional thing later. Okay. Maybe I can actually. Oh, that didn't work very well, did it? I'm sorry. There we go. Okay. So that one right there would be your combustion reaction. Second one. Now this one is an interesting one. This is one we haven't really looked at. So take a look at it. You've got an element, sodium. Don't worry about the coefficients right now. Don't worry that that's a 2 and that's a 2. You can ignore those in terms of classifying reactions. An element plus an element to form a compound. So essentially what you're doing is you're taking simple things and putting them together to make them a bigger thing, right? Does that make sense? You're getting one thing out of two reactants. You're combining things is what you're doing. So for that reason, this is called a combination reaction. A combination reaction is where you take something, combine it with something else, or maybe three things even, although that's pretty rare. And you're making one thing that's more complicated, okay? It doesn't have to be just elements. So for example, there's an example where you have Ca, calcium, which is an element, plus CO2, which is a compound, to form CaCO3. So you're going from element plus a little compound, CO2, to form a big compound, CaCO3. That would be a combination as well. Third one. Now this is one of the examples where you have to be a little bit careful because there's more than one right answer for this one. So you want to click all the right answers. You have a compound here, right? CuSO4. It's a binary ionic compound, metal, nonmetal. Same thing with this one, binary ionic compound, metal with a nonmetal, to form two new binary ionic compounds, right? So this is interesting. Notice how you have a solid over here, right? What if you think back to sections 4.1 and 4.2, precipitation reaction, right? Aqueous salt, aqueous salt, aqueous salt, insoluble salt, right? There's your solid. That's a precipitation reaction right there, okay? But it is also an example of a double replacement. We talked about that as well. When we do precipitation reaction analysis, in particular when we're doing the net ionic equations, we said, look at these compounds as having two parts. So they all have two parts, and you're switching partners, right? The copper is now with the chromate. The zinc here, which was originally with the chromate, but now it's with the sulfate, right? So the zinc is combining with the sulfate, the copper is combining with the chromate. That's a double replacement, sometimes referred to as double displacement. So replacement or displacement means the same thing, okay? So that one is an example where you have two correct answers. You got to click on both of those to get full credit. The last one looks kind of similar to this one here, now that I think about it, right? You got two parts here, it's aqueous, 2 parts here, it's aqueous, 2 parts here, it's aqueous, 2 parts here, solid, right? So there you go. There's your precipitation reaction again. And again, if something is a precipitation reaction, it is also a double replacement. So that one's got 2 parts. Okay. Let me show one more. Here we go. I'm not going to do this one because that one's pretty obvious. This one, same thing. That one right there is a combustion. So that's good. But let's look at these last two here. This one right here, you got a compound, and now that compound is breaking up into smaller pieces. So when does that happen? If you watch TV or you watch movies, when do you see something chemically go from a big piece to a small piece? It's an explosion, right? Explosions do that. Dynamite, which is a mixture of nitroglycerin, this very unstable molecule that as a liquid is very unstable, it's very dangerous. Mix it with a filling compound that is stabilizes, called a stabilizer. Now you have dynamite. Now you have something that's explosive, but it's more stable. You know, if you smack on the, close the door if you close the door really loud, you can blow up nitroglycerin. It's that sensitive. It's very sensitive. But in the form of dynamite is now less sensitive. That's an explosion, right? A big molecule turning into small molecules. Trinitrotoluene is a famous explosive, right? Big molecule breaks up into little molecules. So that's what's happening here. I'm not saying this is explosion, but it is something going from a big molecule, right? It's got 1 potassium, 1 chlorine, 3 oxygens, that's 5 atoms, into 2 smaller things. This one has 2 atoms. This one also has 2. That's called a decomposition, okay? So when you have a big molecule break up into smaller molecules, that's a decomposition. It is typically 1 reactant turning into 2 or 3 products, or 4 products even, but typically 2 or 3, okay? That's decomposition. And then this one right here, well, that's another combustion, right? If you take a look at that one, that's another combustion one. Okay, so there you go. So there's, taking a look at those. I'll just mention that if you have an acid-base reaction, that is also an acid-base reaction, right? You're gonna have your hydrogen like HCl. You're gonna have your NaOH, right, or BaOH2. That is an acid-base reaction. But it's also a double replacement. So acid-base reactions are typically, in addition to being acid-base reactions, they're also double displacement or double replacement reactions, okay? I do want to show one single replacement. So let me see if I can find one in here. We'll look at one more here. Those are all ones we looked at. Maybe they don't give you an option of a single replacement, but it would be nice if they did. Here's when it's acid base, right? You can see that's acid base, but it's also double replacement because the H goes with the OH to make water, and the Na goes with the Cl to make NaCl. So it's double replacement again. I don't see. I'm gonna do one more and see if it pops up. Single replacement. No. Okay, so no single replacement. Okay, so a single replacement. I'll stop share this one. A single replacement, just so that you know. Typically looks like something like this. You have a metal, so an element, reacting with a compound that's typically dissolved in water. Okay, so here's your ionic compound, and then here's your element. So you have an element and a compound. And so what happens is the metal or the element is going to combine with the non-metal. So it's going to combine with the non-metal. And then this metal will be all by itself. Okay, let me balance it. There we go. So you can see that's what it looks like. So this is called single replacement because you essentially got something with 1 part and then something with 2 parts, and they're replacing each other, right? As opposed to the double replacement where you've got, each of the reactants has 2 parts. Okay, so one part, two part, one part, two part. Now you got the chance that you're double replacement. So this one would be double. Here, there's only one part. That's your single replacement. So, you might get something like this, NaNO3, and then COH2. That's a solid, right? That's a precipitation reaction, right? But it's also a double replacement, whereas this one's a single replacement. Okay, there you go. Yeah, we're running a little bit short on time here, but I do want to see, maybe I can just bring up one more problem here. We'll do more of this tomorrow. So let's take a look at this problem. Here we go. Okay, so classify or I'm just going to the top. Identifying acids and bases by their chemical formula, right? Okay, that makes sense. The other one was a little bit ahead of the game, but this makes sense here. Classify each one in the table. So it's either going to be an ionic, a molecular, an acid, base. Now, something could be ionic and a base as well. Something could be molecular and an acid as well. So I'll talk about that in a moment. Okay. So take a look at the formula. You got the hydrogen, non-metal, bunch of oxygens. We talked about that at the beginning, right? Hydrogen, non-metal, bunch of oxygen. That's an acid, right? So that's an acid. Acids are generally considered molecular compounds, even though they have properties that kind of like make them ionic in a sense. They're generally considered molecular compounds. So it's an acid and molecular. Sodium chloride. Okay, well, sodium, you have a metal with a non-metal, so that's an ionic compound for sure. It doesn't have any hydrogen, so it's not an acid. It doesn't have a nitrogen, and it doesn't have an OH, so it's not a base. So this one is not an acid or a base. It's not molecular, right? Molecular is considered the opposite of ionic, right? So molecular, where you have no metals, no ions. This is an ionic compound. Third one, HCl. Okay, well, there you go. That's one of our common acids, right? That's clearly an acid, HCl. But again, acids are generally considered molecular compounds because they're comprised of nonmetals. H2SO4, same thing. That's a sulfuric acid, right? So that's a molecular acid. That's, H2SO4 is molecular and it's an acid as well. Let's see if we have anything else in here. Let's do one more. Very famous base, right? That's the most famous base there is in nature, NaOH, sodium hydroxide, right? So sodium hydroxide is ionic, right? It's got a metal with a non-metal, but it is also a base. Okay, so bases, at least the ones with the hydroxides, those are essentially ionic compounds that have a hydroxide that can dissolve into water. H2SO4, well, we just did that one now. It's your molecular acid. HF, another molecular acid, right? HF, you have your H, you have your F, that's an acid, and it is considered a molecular substance. H3PO4, same thing. Triprotic, right? This one's a triprotic acid or polyprotic acid in general, has the phosphate ion. This one right here is diprotic or polyprotic acid. So we have, actually for this one, we have 3 acids in one base, okay? And there you go. Let's do one more. Okay, same thing, we did H2SO4. Here's another one of the bases, right? Barium hydroxide, it's in that list, right? So it's an ionic base. HI, another acid we've looked at. MgI2, metal, non-metal, no hydroxide in it. So it's, not a base, doesn't have nitrogen in it, right? So metal with a non-metal. So there's your ionic compound. Okay. Let's see here. Okay, so tomorrow what we'll do is we will look at neutralization reactions. So we'll look at this type of problem right here. Notice what we're given here. This is kind of cool. We're given sort of like the precipitation. We're given the reactants, but not told the products. So then the question is, can we predict the products of these reactions? So we'll look at neutralization or acid-base reactions tomorrow. We will, this one right here is called identifying, a little tricky here, identifying whether something is an acid, a strong acid, a base, a weak base, strong base, weak base, based on what happens when you dissolve them into water. So we'll look at that as well. And then finally, This is very similar to the one we just did, where you have a reaction. This is going to be our Bronsted acid reaction. Okay, so we'll look at that tomorrow. Tomorrow is Wednesday, and then Thursday we'll get into assigning oxidation numbers and doing redox chemistry. Those are very energetic reactions. And then next week we'll wrap up this discussion of chapter 4 by looking at concentrations of solutions. Okay, so have a great day. Have a great week. I will talk to you later.